There are an estimated 100 billion stars in our galaxy alone, and more than 2 trillion galaxies in the observable universe. The numbers are so large, they stop meaning anything. If even the tiniest fraction of those stars host planets, and even the tiniest fraction of those planets give rise to life, then the universe should be teeming with it. It should be loud. It should be crowded. The night sky should be alive with the signals of countless civilizations, the glow of engineered stars, the chatter of a galaxy full of voices. And yet, when we point our most sensitive instruments at the sky and listen, we hear nothing. No signals. No structures. No fleets crossing the dark between the stars. Just silence. This is why a physicist named Enrico Fermi, sitting at lunch in the summer of the 1950s, supposedly looked up and asked a question that has haunted science ever since. Where is everybody? It was a simple question, almost casual, the kind of thing you might ask at a dinner table. But beneath that simplicity lay something profound, a contradiction so sharp that decades later we are still struggling to resolve it. On the one hand, everything we know about the universe suggests it should be full of life. On the other hand, everything we observe suggests it is empty. Those two facts cannot both be fully true, and the space between them is one of the deepest mysteries in all of science. It is a question that touches astronomy and biology, physics and philosophy, and ultimately, it is a question about ourselves. Because hidden inside the puzzle of why the universe is silent is a darker question. If something is keeping the galaxy quiet, could that same something be waiting for us? Before we begin, be sure to like the video and subscribe for more journeys into the cosmos. Now, take a deep breath and let's begin. To understand why the silence is so disturbing, you first have to understand just how much time the universe has had to fill itself with life. Our universe is roughly 13.8 billion years old. That is the span from the first moment of the Big Bang to the present day. For most of that time, the cosmos was already capable of producing the ingredients of life. The very first stars ignited only a few 100 million years after the beginning. To put that in proper perspective, the universe spent only a small fraction of its early life in true darkness. In the first moments after the Big Bang, there were no stars at all, only a hot, expanding sea of particles and radiation. As that sea cooled and thinned, gravity began to gather the gas into clumps, and within those clumps, the first stars flickered to life. From that point on, the universe was lit. It has been making stars, and the planets that form alongside them, for more than 13 billion years. These early stars were giants, burning hot and fast, and when they died, they scattered the first heavy elements across space: carbon, oxygen, nitrogen, iron, the building blocks of planets and of biology. By the time our own sun formed, around 4.6 billion years ago, the galaxy had already been seeding itself with these elements for billions of years. Generations of stars had lived, exploded, and died, enriching the gas clouds from which new stars and planets would be born. Every atom of carbon in your body, every atom of oxygen in the air you breathe, every atom of iron in your blood, was forged inside a star that lived and died before our sun was born. These elements did not exist in the early universe. They had to be cooked, slowly, in the nuclear furnaces at the hearts of stars, and then scattered into space when those stars reached the ends of their lives and exploded. Each generation of stars enriched the galaxy a little more, salting the cosmic gas clouds with the ingredients of worlds and of life. By the time enough of these heavy elements had accumulated, the galaxy was ready to build rocky planets like our own. And here is the crucial point. That readiness arrived long before Earth ever formed. This means that planets capable of supporting life could have formed long before Earth ever existed. Some estimates suggest that Earth-like worlds began appearing in our galaxy as much as 8 or 9 billion years ago. If that is true, then there were potentially habitable planets out there for 4 billion years before our world had even cooled. 4 billion years. That is roughly the same amount of time it took life on Earth to go from simple, single-celled organisms to a species capable of building radio telescopes and asking where everyone else is. So consider what that means. If a civilization had arisen on one of those ancient worlds, even just a few billion years before us, it would have had an almost unimaginable head start. While our planet was still a molten ball of rock being bombarded by asteroids, another species could already have been ancient, advanced, and spreading outward into the galaxy. Picture that for a moment. Imagine a world, somewhere in the Milky Way, that formed billions of years before Earth. Life took hold there. It survived its dangerous infancy, climbed the long ladder of complexity, and gave rise to intelligent beings. Those beings built a civilization, developed science, and eventually turned their gaze outward to the stars, just as we have. But while we are only now taking our first steps off our home world, they would have had billions of years to act on that same impulse. By the time the first single-celled organisms appeared in Earth's oceans, that ancient civilization might already have spread across thousands of star systems. By the time the dinosaurs walked our planet, they might have settled an entire arm of the galaxy. By the time our species first learned to make fire, the galaxy might have been thoroughly explored, mapped, and inhabited for an unimaginable span of time. And here is the crucial part. The Milky Way is not actually that big when you think about it in terms of time. Our galaxy is about 100,000 light-years across. That sounds enormous, and in human terms it is. But the galaxy has existed for billions of years. Even a civilization moving at speeds far slower than light, perhaps just 1% of the speed of light, could cross the entire galaxy in a few million years. To us, a few million years sounds like an eternity. It is far longer than our entire species has existed. But to a galaxy that has been turning for more than 13 billion years, a few million years is almost nothing. It is the difference between this moment and the next, on the cosmic clock. Against the backdrop of billions of years of cosmic history, that is the blink of an eye. Imagine a single civilization that learns to build self-sustaining colonies among the stars. It sends out ships to nearby star systems. Those colonies grow, mature, and eventually send out ships of their own. Each new world becomes a stepping stone to the next. This process, repeated over and over, would expand like ripples in a pond. Let me make this picture vivid, because it is the engine that drives the whole paradox. Imagine a single world that achieves interstellar travel. It looks out at the nearest handful of stars and sends settlers, or perhaps just machines, to the most promising of them. The journey takes a long time by our standards, perhaps thousands of years, but the travelers are patient, or the machines simply do not care about the passage of time. Eventually they arrive. They establish a foothold. They gather resources, build, and grow. And after some centuries, this new colony does exactly what its parent did. It looks out at its own nearest stars and sends out the next wave. Now, there are 2 sources of expansion instead of 1. Then 4. Then 8. The frontier does not advance in a straight line. It blossoms outward in every direction. And the number of settled worlds multiplies with each generation of expansion. This is the mathematics of exponential growth, and it is staggeringly powerful. It is the reason that even a slow, patient expansion, with no faster-than-light travel and no exotic physics, would sweep across the entire galaxy in a span of time that is brief compared to the age of the stars. Mathematicians and physicists have run the numbers on this idea, And the conclusion is startling. Even with conservative assumptions, a single determined civilization could colonize the entire Milky Way in something like 10 million years. Possibly less. That is far shorter than the age of the galaxy. Which means that if even one technological civilization had emerged anywhere in our galaxy in the last several billion years, and if it had any interest in spreading outward, it should already be everywhere. It should be on the planet next door. It should have left traces, machines, ruins, beacons. The galaxy should bear the fingerprints of those who came before. And yet, everywhere we look, we find a clean slate. Let me make this concrete, because the scale of the head start is the part that truly unsettles the people who study this. Suppose, somewhere in the Milky Way, a single technological civilization arose just 1 billion years before us. That is not a particularly extreme assumption. Given how long the galaxy has been capable of producing habitable worlds, a head start of 1 billion years is, if anything, modest. 1 billion years is a span of time so vast that it is difficult to hold in the mind. In 1 billion years, continents drift across the face of a planet and reassemble somewhere else entirely. Mountain ranges rise and erode away to nothing. Entire branches of life appear, flourish, and vanish. Now ask yourself what a civilization could accomplish in that amount of time. If it survived, if we, in the span of a single century, went from horse-drawn carriages to landing machines on other worlds, what could a species do with 1 billion years of continuous progress? The honest answer is that we cannot even imagine it. The gap would be so enormous that their works might be indistinguishable from the laws of nature itself. And that is the point. Even if interstellar travel is slow, even if it is difficult and dangerous and expensive, 1 billion years is more than enough time to cross the galaxy many times over. A civilization does not need faster than light travel to spread. It does not need any exotic physics at all. It only needs patience, and the galaxy has provided more than enough of that. The galaxy is roughly 100,000 light-years from edge to edge. A probe traveling at a mere 1% of the speed of light would cross that distance in around 10 million years. That sounds slow to us, but it is a fleeting moment against the age of the galaxy. Send out a wave of self-replicating probes, machines that arrive at a new star system, gather raw materials, build copies of themselves, and send those copies onward, and the wave would spread exponentially. Each settled system becomes a launching point for the next. The expansion accelerates rather than slows. Run that process forward, and the entire galaxy is settled in a few tens of millions of years at most. This is the crux of what makes the silence so loud. It is not that we expect to see one alien signal from one distant world. It is that the galaxy should already be saturated. It should be full to the brim with the descendants and the machines of whoever got there first. We would expect to find their probes drifting through our own solar system. We would expect to see their structures around distant stars, their reshaping of matter and energy on a grand scale, their signals woven through the sky. We would expect, in short, to find a galaxy that has been lived in. There has been time for this to happen not once, but thousands of times over. So when we sweep our telescopes across the sky and find nothing, no probes in our own solar system, no engineered structures around distant stars, no whisper of a signal, we are not just failing to find a neighbor. We are failing to find the consequences of billions of years of cosmic history. This is the heart of the paradox. On one side, we have the sheer scale of the cosmos, the vast stretches of time, the staggering number of stars and planets, all of it screaming that life should be common. On the other side, we have the evidence of our senses and our instruments. Silence. emptiness. A universe that, as far as we can tell, has never once spoken to us. Two truths, each one solid on its own, that seem to contradict each other completely. The mathematics of probability says we should have company. The evidence of observation says we are alone. Something has to give. Either our reasoning about how common life should be is wrong, or our observations are missing something, or there is a hidden factor we have not yet understood. How do we reconcile these two things? That question has launched decades of research, debate, and some of the most unsettling ideas in all of science. To begin to answer it, we need to look more closely at the equation that first tried to put numbers on the problem. In the year 1961, an astronomer named Frank Drake wrote down a simple-looking equation on a chalkboard. It was not meant to give a precise answer. It was meant to organize our ignorance, to break an impossibly large question into smaller, more manageable pieces. This was a profound shift in how we thought about the question. Before this, asking whether we were alone in the universe felt almost unanswerable, too vast and vague to approach with science. What Drake did was take that enormous question and break it apart, like disassembling a complicated machine into its individual components. If you could not estimate the whole, perhaps you could estimate the pieces, one at a time, and then put them back together. It did not provide answers. It provided a framework for thinking clearly, and that, in itself, was a major step forward. The Drake equation asks us to multiply together a series of factors: the rate at which stars form in our galaxy, the fraction of those stars that have planets, the number of those planets that could support life, the fraction of those that actually develop life, the fraction of living worlds where intelligence emerges, the fraction of intelligent species that develop technology capable of sending signals into space, and finally, the length of time such civilizations survive and remain detectable. Multiply all of those together, and you get an estimate for the number of communicating civilizations that should exist in our galaxy right now. The problem is that most of those numbers are almost completely unknown. When Drake first proposed his equation, we did not even know whether planets around other stars were common or rare. We had no examples to go on except our own solar system. Today, that particular piece of the puzzle has changed dramatically. Over the past few decades, astronomers have discovered thousands of planets orbiting other stars. We now know that planets are not rare at all. In fact, they are everywhere. The data suggests that on average, nearly every star in the galaxy hosts at least one planet. Many host several, and a significant fraction of those planets sit in what we call the habitable zone, the region around a star where temperatures could allow liquid water to exist on a surface. When you do the arithmetic, the numbers become almost dizzying. There could be billions of potentially habitable worlds in the Milky Way alone. Billions. It is worth pausing on how recently this knowledge arrived. For nearly all of human history, we had no proof that any planet existed beyond the handful in our own solar system. The first confirmed discovery of a planet orbiting a sun-like star came only in the 1990s. Before that, planets beyond our system were a matter of faith and reasonable assumption, but not of evidence. Then came a flood. Dedicated space telescopes stared at single patches of sky, watching tens of thousands of stars at once, looking for the tiny, regular dimming that happens when a planet passes in front of its star. The dimming is faint, often a fraction of a percent, but it is unmistakable, and it repeats with the rhythm of an orbit. World after world revealed itself this way. Small rocky planets, vast gas giants. Worlds orbiting so close to their stars that their surfaces are oceans of molten rock. Worlds drifting in the cold outer dark. And, crucially, worlds sitting in the temperate band where liquid water could pool on a surface. From these surveys, astronomers were able to estimate how common such worlds are across the entire galaxy. The conclusion was that rocky planets in the habitable zone are not exotic at all. They may number in the billions. In other words, the cosmic stage is set. The theater has billions of seats. The lights are on. The only thing missing is any sign of an audience. So the first few factors in the Drake equation, the ones about stars and planets, have turned out to be encouraging. The raw real estate for life appears to be abundant, but the equation does not end there. The later terms are where everything becomes uncertain and where the real mystery lives. We do not know how often life actually begins on a suitable world. We have exactly one example of life arising, and that is here on Earth. A sample size of 1 tells us almost nothing. Life might be a near inevitability, springing up wherever conditions allow. Or it might be an extraordinary fluke, a 1 in a trillion accident that has happened only once in the entire history of the universe. We simply cannot tell from where we stand. To appreciate how mysterious the origin of life truly is, consider what actually had to happen. On the early Earth, there was no life. There were only chemicals, water, gases, minerals, energy from lightning and from the young sun, all churning together in the oceans and the atmosphere of a violent young world. Somehow, out of that chaos, molecules arose that could copy themselves. A molecule that builds a copy of itself, which then builds another copy, and another, is the seed from which all of biology grows. But how that first self-copying molecule came to be is one of the deepest unsolved problems in all of science. We have ideas. We have promising experiments that show how some of the building blocks of life can form on their own under the right conditions. But the full leap from a soup of ingredients to a living, reproducing system has never been bridged in a laboratory and never been observed anywhere in nature except in its finished form. It may be that this leap is easy, happening readily on any world with the right ingredients and enough time. Or it may be that it requires a precise and improbable sequence of events, a roll of the dice that almost never comes up right. We genuinely do not know. And that single uncertainty alone is enough to swing the answer to the Fermi paradox from a crowded galaxy to an empty one. And even if life is common, intelligence is another matter entirely. Life existed on Earth for billions of years as nothing more than microbes, simple cells, drifting and dividing, with no brains, no tools, no curiosity. It took an enormous span of time for complex life to evolve, and even longer for anything resembling intelligence to appear. For most of our planet's history, there was no one here capable of looking up and wondering about the stars. Think about the timeline of our own world. Life appeared on Earth surprisingly early, within the first billion years or so after the planet formed. That fact alone might suggest that simple life is easy. But then came an enormous, almost unimaginable pause. For something like 2 billion years, life on Earth went almost nowhere. It remained simple. Tiny cells, drifting in the seas, dividing and multiplying, but never combining into anything more complex. 2 billion years of stagnation. That is nearly half the age of our entire planet, spent in a holding pattern. Whatever it took to break out of that pattern was clearly difficult. This long stagnation is one of the most telling facts in the entire story. It tells us that the mere presence of life on a world does not guarantee progress. Life can persist for billions of years, perfectly successful in its own way, without ever becoming more complex. For 2 billion years on Earth, life did exactly that. It survived. It thrived. It covered the planet, but it remained simple, single, and small. If that long pause is typical, then most living worlds in the galaxy might never advance beyond it at all. They might be covered in life, oceans and rocks teeming with microbes, and yet remain forever silent, with nothing on them ever growing complex enough to look up at the stars. And when complex life finally did arise, it was not a steady march toward intelligence. It was a wild, branching, chaotic experiment, full of dead ends and disasters. For hundreds of millions of years, the most advanced creatures on Earth were fish, then reptiles, then the great dinosaurs. None of them developed technology. None of them built radio telescopes or asked where everyone else was. They were superbly adapted, dominant, and successful, and they ruled the planet for far longer than mammals have. Yet intelligence of our kind never emerged among them. It took a catastrophe, the impact that ended the age of the dinosaurs, to clear the stage and give our small mammalian ancestors their chance. And even then, it took tens of millions more years for that chance to produce a creature that could think the way we do. The point is this: even on a world where life took hold early and thrived for billions of years, intelligence capable of building a civilization appeared only once, late, and seemingly by a long chain of accidents. If that chain is as unlikely as it appears, then a galaxy full of living worlds might still contain almost no one to talk to. If the path from simple life to intelligent life is rare or difficult, then even a galaxy full of living worlds might contain very few thinking beings. And the final terms are perhaps the most troubling of all. Even if intelligent life arises, will it develop technology? And if it does, how long will that technology last? A civilization might rise, build, broadcast, and then collapse, all within a few thousand years. Against the billions of years the galaxy has existed, a few thousand years of activity is nothing. A flicker, a spark that dies before anyone notices it. This last point bears repeating, because it is the quiet killer hidden inside the whole equation. Even in the most optimistic scenario, where life is common and intelligence frequent and technology routine, everything still depends on how long a civilization lasts. If the typical technological civilization survives for only a few thousand years before destroying itself or fading away, then at any given moment, the number of civilizations actually broadcasting and detectable might be tiny. They would be scattered thinly across both space and time, each one a brief flame, rarely overlapping with another. But if civilizations routinely survive for millions of years, learning to manage their power and stabilize their worlds, then the galaxy could be rich with them, and the silence would become genuinely baffling. So that final term, the lifespan of a civilization, may be the most important number of all. It is, in a sense, a question about us. How long will we last? We have been a technological, broadcasting civilization for barely 100 years. Whether that number turns out to be 100, or 1,000, or 1,000,000, may decide not only our own fate, but whether we ever have company in the cosmos. So, the Drake equation, for all its elegance, leaves us hanging. Depending on what values you plug in, it can predict a galaxy crawling with millions of civilizations, or a galaxy where we are utterly and completely alone. The equation does not solve the paradox. It sharpens it. It takes a vague unease and gives it a precise shape. It shows us exactly where the uncertainty lives and forces us to look directly at the gaps in our knowledge rather than glossing over them. And in doing so, it makes the silence feel even stranger, because it reveals just how many ways the galaxy could be full of life, and just how few of those ways we can actually rule out. It tells us exactly where our ignorance lies, and it forces us to confront an uncomfortable truth. Somewhere in that chain of factors, something is filtering out the civilizations. Something is keeping the galaxy quiet. The question is, what? And to find the answer, scientists began proposing solutions, dozens of them. Some comforting, some strange, and a few that are genuinely terrifying. Let us start with the gentlest explanations, the ones that let us keep our sense of optimism before we descend into darker territory. One of the simplest possibilities is that we are simply not listening in the right way. The universe is vast, and our search for signals from other civilizations has been, by cosmic standards, almost laughably brief and limited. Serious efforts to detect alien radio transmissions began only in the 1960s. That means we have been actively listening for less than a single human lifetime. Compared to the billions of years the galaxy has existed, our search has lasted barely an instant. And it is not just that we have been listening for a short time. We have also been listening to a tiny fraction of the sky across a narrow range of frequencies, with instruments of limited sensitivity. One researcher offered a useful comparison. Imagine searching for fish in all the world's oceans, but only ever dipping a single drinking glass into the water, just once. If you pulled that glass out and found no fish, would you conclude the oceans were empty? Of course not. You would conclude that you had barely begun to look. That is roughly where we stand in our search for extraterrestrial signals. The scale of the mismatch is hard to overstate. The galaxy contains hundreds of billions of stars. We have closely examined only a tiny handful of them for signs of artificial signals. There are countless radio frequencies on which a civilization might transmit, and we have listened to only a narrow slice of them. A signal might come at any time, in any direction, on any frequency, and last for any duration. To catch it, we would need to be pointed at the right star, tuned to the right frequency, at the right moment, with a sensitive enough instrument to detect a faint whisper across the gulf of light years. The odds of all of those conditions lining up, given how little of the search we have completed, are slim. We have dipped our glass into the cosmic ocean a handful of times and found it empty. That tells us very little about whether the ocean itself contains life. There is also the problem of what we are even listening for. Our search has focused largely on radio waves, because that is the technology we developed first and understand best. But radio is just one narrow band of the electromagnetic spectrum. An advanced civilization might communicate using methods we have not even imagined. They might use tightly focused laser pulses. They might compress their signals so efficiently that, to an outside observer, they would be indistinguishable from random noise. They might use physics we have not yet discovered. Even our own civilization is becoming quieter over time. A century ago, we blasted powerful, sloppy radio signals in all directions. Today, we increasingly use tight beams, cables, and efficient digital transmissions that leak very little energy into space. If the trend continues, Earth itself may become nearly invisible to anyone listening from far away within a few generations. There is an irony in this worth noting. The window during which a civilization broadcasts loudly and carelessly into space may be remarkably short. For us, it has lasted only about a century, and it may already be closing. As our technology matures, we leak less and less energy into the cosmos. If this is a general pattern, then every civilization might have only a brief, noisy adolescence, a few decades during which it shouts into the void before quieting down again. If that window is short enough, then catching another civilization during its loud phase, at exactly the right moment, across the vast distances of space, would be extraordinarily unlikely. The galaxy could be dotted with civilizations that each broadcast loudly for a brief moment in cosmic time, and then fell quiet, their windows never overlapping with our own. So perhaps the galaxy is full of conversations, and we simply lack the right equipment, the right frequencies, or the right amount of patience to hear them. There is also the brutal problem of distance and time working against us. Even if a civilization is broadcasting right now from a star 1,000 light-years away, the signal we receive today left that world 1,000 years ago. And the signal we send today will not arrive for another 1,000 years. A conversation conducted across such distances is not a conversation at all. It is a series of messages flung into a void, with the senders long gone by the time any reply could arrive. Two civilizations could exist in the same galaxy, each broadcasting eagerly, and still miss each other entirely, simply because their signals are passing through empty space during the brief windows when the other happens to be listening. There is also the matter of timing on the largest scale. For two civilizations to detect one another, they must overlap not just in space, but in time. A species might rise, broadcast for a few thousand years, and fall silent again, all long before another species nearby ever develops the ability to listen. The galaxy has existed for billions of years. A technological window of a few thousand years is a candle lit and snuffed out in the dark. For two such candles to be burning at the same moment, close enough to see each other, may be extraordinarily rare, even if many candles have flickered over cosmic history. This is a comforting thought. It suggests the silence is an illusion, a product of our own limitations rather than a true absence. But it does not fully satisfy the paradox. Because remember, the issue is not just radio signals. The issue is that a sufficiently old and ambitious civilization should have physically spread across the galaxy by now. Even if they were silent, we would expect to see their structures, their probes, their colonies. Listening harder does not explain why the galaxy appears physically untouched. So we need to dig deeper. A second gentle explanation is that intelligent life simply does not want to be found, or does not want to expand. Perhaps the assumption that any civilization would naturally spread outward and colonize the stars is wrong. That assumption is based largely on our own history, on the way humans have explored and settled new lands. But an alien intelligence might be nothing like us. We tend to imagine that any intelligent species would share our restlessness, our hunger to explore and expand, our drive to fill every available space. But these are features of our particular history and psychology, shaped by the specific pressures that formed our species. A different intelligence, arising under different conditions, might have no such drive at all. It might value stability over growth, contemplation over conquest, depth over expansion. To project our own restless nature onto every possible mind in the cosmos may be a profound mistake. A civilization might reach a point of contentment, choosing to live quietly within its own star system, with no desire to conquer the galaxy. It might turn inward, building elaborate virtual worlds and simulated realities that are far more appealing than the cold, empty distances between the stars. This idea is more plausible than it might first sound. Consider what actually drives a civilization to expand. For much of our own history, exploration was driven by the search for resources, for land, for wealth, for survival. But a sufficiently advanced civilization might solve all of those problems at home. If you can generate all the energy you need from your own star, produce all the materials you require, and create experiences richer than any reality through technology, then the brutal cost of crossing the void between stars begins to look pointless. Why endure thousands of years of travel through empty space to reach a cold and barren world when you could build whatever you desire in the comfort of your own system. A civilization might reach a kind of maturity in which the restless urge to expand simply fades away. It becomes content. It turns its energy inward, toward art, toward thought, toward the cultivation of its own inner worlds. If this is the common fate of advanced civilizations, then the galaxy could be dotted with quiet, contented species, each one absorbed in its own affairs, none of them bothering to announce itself or reach across the dark. The galaxy would be inhabited, but it would still be silent. Why cross thousands of light-years of vacuum when you can create a perfect universe inside a computer? Some have suggested that advanced civilizations might deliberately hide. This idea has a darker flavor to it, and we will return to it later. But the gentle version simply proposes that mature civilizations value privacy or stability over expansion. There is also the possibility that we are being observed, and the silence is intentional. This is sometimes called the zoo hypothesis. The idea is that advanced civilizations know we are here, but have agreed to leave us alone, the way a nature reserve leaves wild animals undisturbed. They watch from a distance, careful not to interfere with our development, perhaps waiting until we reach some threshold of maturity before making contact. There are gentler and darker versions of this idea. In the gentler version, we are like a developing child, protected and observed, allowed to grow at our own pace until we are ready to join some larger community of minds. The silence, in this telling, is an act of care, a deliberate restraint, a refusal to overwhelm a young civilization before it can stand on its own. Perhaps there is even a threshold we have not yet crossed, a sign of maturity they are waiting for, after which the silence will finally break and we will be welcomed. In the darker version, we are less a child being raised than a specimen being studied. A curiosity in a vast cosmic collection, observed from behind glass we cannot see. Our every signal noted, our development tracked, but contact forever withheld because we are simply more interesting left wild. Both versions share the same haunting implication. It is an appealing thought in some ways, and an unsettling one in others. It would mean we are not alone, but that we are being managed, contained, kept in the dark for reasons we cannot know. The trouble with these explanations is that they require every single civilization to behave the same way. For the zoo hypothesis to work, every advanced species in the galaxy would have to agree to stay hidden, with no exceptions, for millions of years. It only takes one civilization to break the pattern. There is yet another angle to this, one that deepens the mystery rather than resolving it. If advanced civilizations exist and choose not to expand physically, we might still expect to see evidence of their energy use. A civilization that grows in power needs ever more energy, and the most abundant source of energy in any star system is the star itself. Thinkers have long imagined that a sufficiently advanced civilization might build vast structures to capture the light of its star, surrounding it partially or even entirely to harvest its output. Such a structure would betray its presence in a particular way. The star would shine strangely, dimmed in visible light, but glowing with waste heat in the infrared part of the spectrum. Astronomers have searched for exactly this signature. They have examined enormous numbers of stars and even surveyed entire distant galaxies, looking for the telltale glow of a civilization that has harnessed the power of its suns. The result, so far, has been nothing. No stars dimmed by orbiting energy collectors. No galaxies blazing with the infrared waste heat of a civilization gone galactic. This is significant because such structures would be visible across vast distances, far beyond the range at which we could ever detect a radio signal. A civilization does not need to be trying to contact us for us to notice it remaking its star. And yet the sky shows us only natural starlight, behaving exactly as the laws of physics predict, with no sign that anyone, anywhere, has reached up to harness it. It only takes one civilization to break the pattern. The fact that we see nothing at all suggests either that there is no one out there to break the pattern, or that something prevents anyone from ever reaching that point. And this brings us to the most powerful and most disturbing idea in the entire discussion. A concept that ties all of these threads together and offers a single, chilling explanation for the silence. It is called the Great Filter. Imagine the entire journey from lifeless matter to a galaxy-spanning civilization as a long obstacle course. At the starting line, you have nothing but the raw ingredients, simple chemicals on a young planet. At the finish line, you have a civilization advanced enough to spread across the stars and announce its presence to the cosmos. Between those 2 points lie a series of hurdles: the formation of the first self-replicating molecules, the emergence of simple cells, the leap to complex cells, the development of multicellular life, the evolution of intelligence, the invention of technology, and finally, the survival of that technological civilization long enough to make its mark on the galaxy. Each of these hurdles is worth dwelling on because the obstacle course is longer and more treacherous than it first appears. Consider the very first rung. A young planet, rich in chemistry, must somehow give rise to the first molecule capable of copying itself. We have already seen how mysterious that step is, how we have never witnessed it nor recreated it. It may be the hardest step of all, or it may be trivially easy. We have no way to know with a sample size of 1. Then comes the rise of the simple cell, a self-contained unit of life with a boundary separating its inside from the outside world. Then the leap to the complex cell, the kind that makes up plants and animals, which on Earth happened only once in 4 billion years. Then the emergence of many-celled organisms, creatures built from countless cells working together. Then the slow evolution of nervous systems, of brains, of the capacity to learn and remember and plan. Then the rare flowering of intelligence, sharp enough to build tools, to use language, to pass knowledge from one generation to the next. Then the invention of technology, of science, of the means to peer beyond one's own world. And then, finally, the longest and perhaps most dangerous step of all. The challenge of surviving with that technology, of not destroying oneself, for the millions of years needed to truly spread across the stars. Every one of these steps had to be cleared in sequence to produce us. Miss anyone, and the chain breaks. The galaxy could be littered with worlds that made it partway and then stalled. Worlds of nothing but microbes. Worlds of complex life that never developed intelligence. Worlds of intelligent creatures that never built technology. Worlds of technological civilizations that flared briefly and then went dark. The Great Filter is the idea that somewhere along this obstacle course, there is at least one hurdle that is almost impossible to clear. A step so difficult, so improbable, that almost nothing ever makes it past. That filter would explain the silence perfectly. If there is some stage in the journey that virtually no life ever survives, then the galaxy would naturally be empty of advanced civilizations. No matter how many planets exist, the filter would act like a wall, stopping almost everything before it ever reaches the stars. Now here is where the idea becomes genuinely frightening. The crucial question is not whether the filter exists. The crucial question is where the filter lies. Is it behind us, or is it ahead of us? This single question may be the most important one our species can ask. And almost no one outside of a few scientists and thinkers has ever even considered it. It does not concern itself with the past alone, or with abstract curiosity about aliens. It is, at its core, a question about whether we have a future. Think carefully about what each possibility means. If the great filter is behind us, then it represents some step that we have already passed. Some incredibly unlikely event in our history that almost nothing else in the universe has managed to replicate. Perhaps it was the very origin of life itself. The transition from non-living chemistry to the first living, reproducing cell may be staggeringly rare. We know it happened at least once, here on Earth, but we do not know how. We have never observed it happening anywhere else, and we have never managed to recreate it from scratch in a laboratory. It is possible that this single step, the spark of life, is so improbable that it occurs on only one world in a galaxy, or one world in 1,000 galaxies. If that is the case, then we have already cleared the hardest hurdle. We are the lucky ones, the rare survivors, and the silence simply reflects how alone we truly are. There is a strange comfort in this idea, even as it isolates us. It would mean that the long, improbable chain of events that led from lifeless chemistry to a thinking, questioning species is something we have already completed. The hardest part would be behind us, not ahead. The danger would have been at the very beginning, in that first impossible spark, and we would have survived it simply by existing at all. Or perhaps the filter was a later step, the jump from simple cells to complex cells. On Earth, this transition happened only once, and it took an astonishingly long time. For billions of years, life on our planet consisted of nothing but simple cells. Then, in a single extraordinary event, one cell engulfed another, and instead of digesting it, kept it alive inside itself. That partnership became the foundation of all complex life. Every plant, every animal, every fungus descends from that one improbable merger. Think about what that means. In 4 billion years of life on Earth, with countless trillions of cells dividing and competing and evolving, this particular leap, the merging of two simple cells into one complex cell, appears to have succeeded only a single time. Everything you have ever seen with your eyes, every tree, every bird, every blade of grass, every other human being, traces back to that one event. If it had not happened, Earth might still be a living world, but a world of nothing but slime and scum, microbes coating the rocks and floating in the seas, with no creature ever growing large enough or complex enough to look up at the sky. A step that happens only once in 4 billion years, on a planet absolutely saturated with life, is a very good candidate for a filter. It might be that this transition is so rare that most living worlds never make it past the microbial stage at all. A galaxy that looks empty might in fact be quietly teeming with simple life, none of it ever advancing, all of it stuck behind the same invisible wall. If that event was a fluke, a once-in-a-universe accident, then it too could be the great filter. A wall that life almost never climbs. If any of these explanations are correct, then the news is, paradoxically, good for us. A filter behind us means the hard part is over. It means our existence is a triumph against staggering odds, and our future is open. We could be the first, and perhaps the only, civilization to ever reach this point in our galaxy. The stars would be ours to inherit, with no one to stop us. In this version of events, the loneliness of the universe is not a tragedy but a triumph. It would mean we had already passed through the deadliest part of the gauntlet, survived the step that ended everyone else, and emerged on the far side into an open future. The empty galaxy would not be a warning, but a vast and welcoming frontier, waiting for the rare civilization fortunate enough to reach it. And we might be that civilization. But there is another possibility. A possibility that has kept scientists and philosophers awake at night. What if the great filter is not behind us? What if it lies ahead? If the filter is in our future, then it means the hard steps, the origin of life, the rise of complexity, the dawn of intelligence, are actually relatively easy. It means the galaxy has produced life and intelligence many times over. Countless civilizations have risen, just as we have, full of ambition and curiosity, reaching out toward the stars. And then, something stopped them. Every single one of them, without exception. The same wall that ended all the others would be waiting for us as well, somewhere just ahead on the path we are walking. If the filter is ahead, it represents some obstacle that no civilization has ever survived. A trap that catches everyone, sooner or later, before they can spread across the galaxy. And if that is true, then we are approaching that trap right now. We would be just one more civilization marching confidently toward a wall that has ended all the others. The silence of the universe, in this reading, is not a sign of our loneliness. It is a warning. A galaxy littered with the ruins of those who came before, all of them stopped at the same invisible barrier. Imagine it. World after world where intelligence flickered into being, reached for the stars, and then went dark. Each one convinced, as it climbed, that it would be the one to make it. Each one, in the end, joining the silent majority. If that is the true shape of cosmic history, then the quiet sky above us is not empty. It is a memorial. This is why the Fermi paradox is more than an academic curiosity. The location of the great filter is, in a very real sense, a question about our own survival. And the evidence we gather in the coming years may tell us which side of the filter we are on. It is worth sitting with just how strange this situation is. In almost every other area of science, discovering that we are not alone, that the universe is full of life and activity, would be cause for joy. But here, the logic runs backward. If the universe turns out to be brimming with life, then the absence of advanced civilizations becomes harder and harder to explain by chance. It would mean that life arises easily, that intelligence is common, and yet that something, somewhere, reliably stops every civilization before it can spread, and that something would still be waiting for us. The more crowded the early stages of life turn out to be, the more certain it becomes that the filter lies in the late stages. In the stage we are entering right now. This is the cruel twist at the center of the Fermi paradox. Good news about life in the universe might be terrible news about our own future, and a lonely, barren cosmos might be the most reassuring thing we could possibly discover. To understand why a filter ahead of us is so plausible, we have to look honestly at the dangers that any technological civilization faces. Because the unsettling truth is that the very things that make a civilization advanced are also the things that can destroy it. Consider the path that we ourselves have walked. For most of human history, our species had no power to threaten its own existence. A tribe could fail, a city could fall, but humanity as a whole was never in danger from its own hands. Then, in a remarkably short span of time, that changed. Within a single century, we developed the ability to wipe ourselves out. The discovery of nuclear weapons gave a single species, for the first time, the power to end its own story in an afternoon. During the tensest moments of the 20th century, the world came closer to that edge than most people realize. There were false alarms. There were misunderstandings. There were moments when the decision to hold back rested on the judgment of a single individual, choosing not to act on a warning that turned out to be a computer error. We survived those moments. It is worth pausing on how thin the margin sometimes was. On more than one occasion, the early warning systems built to detect an incoming attack reported that one was underway, when in fact nothing of the kind was happening. A reflection of sunlight off high clouds, a flock of birds, a faulty piece of equipment feeding bad information into the machinery of war. In those moments, the fate of much of the world rested on the judgment of individuals who had only minutes to decide whether the warning was real, and who chose, against protocol and against the screaming of their instruments, to wait, to not act, to assume it was a mistake, and they were right. But they might not have been. That a global catastrophe was avoided by the calm judgment of a single person under unimaginable pressure in the span of a few minutes should give us pause. It suggests that the survival of a civilization through its most dangerous period may depend on factors that are perilously fragile. A civilization does not need to want to end itself. It needs only to make one fatal error, on one bad day, at the wrong moment, after gaining the power to do so. But survival was not guaranteed. It was, in some cases, a matter of luck. There is a phrase that captures this danger well. It is the gap between knowledge and wisdom. A civilization's knowledge, its raw technical power, tends to grow explosively, faster and faster as each discovery enables the next. But wisdom, the judgment to use that power well, grows slowly, painfully, through hard experience and often through tragedy. These two things do not grow at the same rate. Knowledge can leap forward in a single generation, transforming a society from one that fights with simple tools to one that can shatter cities in an instant. But wisdom cannot be downloaded or invented overnight. It must be earned, slowly, through the accumulated lessons of those who came before. For a long stretch of a civilization's development, knowledge races far ahead of wisdom. The species can do things it is not yet mature enough to do safely. That gap is the danger zone. It is the period in which a civilization holds the power to destroy itself, but has not yet learned the restraint to avoid it. If most civilizations enter that danger zone, and if even a modest fraction of them fail to make it through, then the galaxy would be full of worlds that reached for greatness and fell. Now imagine this pattern playing out across the galaxy. A civilization climbs the ladder of technology. It learns to split the atom. It gains the power to reshape its world, and also the power to destroy it. If even a fraction of civilizations, upon reaching that threshold, fail to control their new power, then the galaxy would be full of worlds that briefly flared with intelligence and then went dark. And nuclear weapons are only the beginning. A sufficiently advanced civilization unlocks one dangerous technology after another. The ability to engineer life itself, which could be used to cure disease or to create something that escapes control. The ability to alter a planet's climate, which can happen by accident long before it happens by design. The creation of artificial intelligence that may eventually surpass its makers, with goals that no longer align with their own. Each of these deserves a closer look, because each represents a doorway that, once opened, cannot easily be closed. Take the engineering of life. A civilization that learns to read and rewrite the code of its own biology gains the power to cure every disease, to end hunger, to reshape itself for the better. But the same knowledge could be used, by accident or by intent, to create something that spreads beyond all control. A single mistake in such a powerful technology could, in principle, threaten an entire species. Take the reshaping of a planet's climate. A civilization growing in power inevitably alters the world it lives on. It burns fuels. It changes the composition of its atmosphere. It warms or cools its planet without fully intending to. By the time the consequences become undeniable, they may already be difficult to reverse. A civilization can damage the very life support system of its home world simply by growing without ever firing a single weapon. And take the creation of minds greater than one's own. A species that builds a true artificial intelligence, something that can improve itself and reason beyond the level of its creators, is taking a profound gamble. If the goals of that intelligence do not align perfectly with the well-being of its makers, the results could be catastrophic, and there might be no second chance to correct the mistake. Each new power is a double-edged sword. Each one offers tremendous benefits, and each one carries the seed of catastrophe. Perhaps the great filter is not a single obstacle, but a gauntlet. A series of self-inflicted dangers that civilizations must navigate, one after another, with no room for error. And perhaps the odds of surviving all of them, every single one, without a fatal mistake, are simply too low. Consider what it means to face not one such danger, but a whole succession of them. A civilization survives its first brush with self-destruction, only to develop a new and more powerful technology that brings new dangers. It survives that one too, and then another arrives, and another. Each crossing must be made successfully. A single failure at any one of them ends the story. The longer a civilization advances, the more of these gauntlets it must run, and the more chances there are for something to go fatally wrong. It is a little like asking someone to cross a busy road blindfolded, over and over again, for thousands of years. Even if they succeed nearly every time, eventually, on one crossing, their luck runs out. There is a chilling logic to this idea. The same intelligence that allows a species to build a civilization is the intelligence that allows it to build weapons. The same curiosity that drives discovery is the curiosity that opens dangerous doors. A civilization cannot reach the stars without first developing the very powers that could destroy it. There is no shortcut around this. You cannot build a starship without first mastering enormous energies. And the mastery of enormous energies is also the mastery of enormous destruction. You cannot understand the workings of life well enough to spread it among the stars without also understanding it well enough to end it. The knowledge that lifts a civilization upward is the same knowledge that could bring it crashing down. The filter, in other words, may be built into the nature of intelligence itself. It may be that any species smart enough to leave its home world is also smart enough to end itself, and that the second outcome almost always arrives first. This is perhaps the bleakest version of the entire paradox. It suggests that the very qualities that make a civilization capable of reaching the stars, its intelligence, its ambition, its relentless drive to understand and to build, are inseparable from the qualities that make it capable of destroying itself. You cannot have one without the other. A species placid enough to never pose a danger to itself might also be too placid to ever develop technology in the first place. A species driven enough to build starships might also be driven enough to build the weapons that end its story. If this is true, then the filter is not an accident or a stroke of bad luck. It is woven into the very logic of how intelligence arises and grows. It would mean that the galaxy falls silent, not because civilizations are unlucky, but because they are, in a sense, doing exactly what intelligent civilizations do: reaching, building, and then, again and again, going dark. There is also the slow filter, not a sudden explosion, but a gradual collapse. A civilization might exhaust the resources of its planet faster than it can find new ones. It might poison its own environment, or destabilize the delicate systems that kept it alive. It might fracture into conflict over dwindling supplies. None of these endings require a single dramatic moment. They are the kind of slow unraveling that a civilization might not even recognize until it is too late. This may, in fact, be the more likely kind of ending. We tend to imagine the end of a civilization as a single dramatic catastrophe, a flash and then darkness. But history suggests that most things end not with an explosion, but with a slow erosion. A civilization might simply grow faster than its resources allow. It might consume the easy energy and the rich materials of its home world and find that what remains is harder and harder to reach. It might foul its own environment so gradually that no single generation notices the change, each one accepting a slightly more degraded world as normal. It might fracture under the strain, its people turning against one another as the comforts they had grown used to begin to slip away. None of this requires a villain or a single fatal mistake. It requires only the ordinary momentum of growth, continued past the point that the world can sustain. A civilization could decline not because it was foolish, but because the very success that let it flourish carried within it the seeds of its own limits. And a civilization in slow decline does not spread across the galaxy. It turns inward, struggling to hold itself together, with no energy left for the stars. When we look at our own world, we can see the early shapes of these dangers, the strain on our environment, the competition for resources, the accumulating risks of our own technologies. We are not pointing this out to alarm, but to observe honestly. We are a young civilization, and we have only just begun to grapple with the consequences of our own power. We have changed the composition of our atmosphere. We have transformed the surface of our planet. We have built tools capable of great good and great harm, often faster than we have built the wisdom to wield them. None of this means we are doomed. But it does mean that we are, right now, living through exactly the kind of period that the Great Filter describes. A period of rapidly growing power, not yet matched by a corresponding growth in restraint and foresight. It is not difficult to imagine how a civilization could stumble. What is difficult is imagining how one could navigate every single one of these threats perfectly for the millions of years required to truly secure its future. If the Great Filter lies ahead, this is most likely where it lives. Not in some external disaster, but in the gap between a civilization's power and its wisdom. The window in which a species has gained the ability to destroy itself, but has not yet gained the maturity to avoid doing so. We are, right now, inside that window. We crossed into it the moment we built our first world-ending weapon, and we have not yet found our way out. We have been inside this dangerous window for less than a century. In that brief time, we have already come close to the edge more than once. We do not know how wide this window is, or how long a civilization can survive within it before its luck runs out. What we do know is that we are in it right now, today, holding powers our ancestors could not have dreamed of, still learning how to wield them without harming ourselves. This is the sobering possibility that the silence of the universe forces us to consider. That the empty sky is not empty because life is rare, but because life, again and again, has destroyed itself at almost exactly the stage we have now reached. But the dangers a civilization brings upon itself are not the only threats out there. The universe itself is a far more hostile place than it appears from the comfort of our blue and green world. And some of the filters may come not from within, but from the cosmos around us. For all its beauty, the universe is filled with forces capable of erasing life on a planetary scale. We live on a world that has been, by cosmic standards, remarkably lucky and remarkably stable. But that stability is not guaranteed anywhere, and the history of our own planet shows how fragile it truly is. Earth has suffered through at least 5 mass extinctions, events in which the majority of all living species were wiped out. 5 times in the history of our planet, life has come close to being erased. 5 times, the great web of living things was torn apart, and the survivors had to rebuild from a fraction of what had existed before. These were not gentle transitions. They were planet-wide catastrophes, each one reshaping the entire course of life on Earth. And our world is one of the lucky ones, a stable planet in a quiet corner of the galaxy. If even a sheltered world like ours has come so close to losing everything so many times, then the universe must be a far more dangerous place for life than it appears from the safety of a single calm afternoon. The most famous of these ended the age of the dinosaurs. Around 66 million years ago, an asteroid roughly 10 kilometers wide struck our planet. The impact released energy beyond anything in human experience. It threw enough debris into the atmosphere to darken the skies across the entire globe. Plants withered without sunlight. Food chains collapsed. The great reptiles that had ruled the Earth for over 100 million years were gone. Consider the sheer randomness of it. For more than 100 million years, the dinosaurs had been the undisputed masters of our planet. They had survived for far longer than mammals have existed. They were diverse, successful, perfectly adapted to their world. And then, in a single moment, a rock from space arrived and ended their long reign. Not because they had done anything wrong, not because they were unfit, simply because they happened to be living on a planet when an object from the depths of the solar system crossed its path. That single rock, falling from the sky, reset the entire course of life on our planet. Had it not struck, mammals might never have risen to dominance, and we might never have existed at all. Now consider that the galaxy is full of such rocks. Asteroids and comets drift through space in vast numbers, and over millions of years, collisions are not a matter of if, but when. A young civilization that has not yet developed the means to detect and deflect such objects is entirely at the mercy of chance. A single large impact could undo millions of years of progress in an afternoon. This is not a distant or theoretical danger. Our own solar system is still full of debris left over from its formation. Countless objects, from pebbles to mountains, drift on long orbits that occasionally cross the path of our planet. Most of the large ones have been swept up or flung away over the billions of years since the system formed, but not all. It is only very recently, within the last few decades, that our species has even begun to systematically search the sky for objects that might one day strike us. And it is only now that we are taking the first tentative steps toward developing the ability to deflect such an object, should we ever find one, on a collision course. For most of our history, we were utterly defenseless, just as every young civilization must be. A planet must survive long enough and develop quickly enough to gain the power to protect itself from the very debris of its own creation. Many worlds may not get that chance. A civilization could be wiped from existence by a single rock after billions of years of careful progress, simply because it had not yet learned to watch the sky. But asteroids are only one of the cosmic threats. The stars themselves can be deadly. When a massive star reaches the end of its life, it explodes in a supernova, briefly outshining an entire galaxy. If such an explosion occurred close enough to an inhabited planet, the burst of radiation could strip away the planet's protective atmosphere and bathe its surface in lethal energy. Even more violent are the events we call gamma-ray bursts. These are the most powerful explosions known in the universe. Focused beams of radiation released when certain massive stars collapse, or when dense stellar remnants collide. For a few brief seconds, A single gamma-ray burst can release more energy than our sun will produce in its entire lifetime of billions of years. And unlike an ordinary explosion that spreads its energy in all directions, a gamma-ray burst is focused, channeled into narrow beams that lance outward across the cosmos. If one of those beams happened to be pointed at an inhabited world, the consequences would be catastrophic, even from an enormous distance. The radiation would tear apart the protective layers of the planet's atmosphere, exposing the surface to deadly energy from its own star and from space itself. The chemistry that sustains life could be disrupted across an entire hemisphere in moments. A gamma-ray burst, pointed directly at an inhabited world from within its own galaxy, could devastate life across the planet, even from thousands of light-years away. Some scientists have wondered whether one of Earth's ancient extinction events might have been triggered by exactly such a cosmic catastrophe. There is reason to take this seriously. One of Earth's earlier mass extinctions, long before the one that ended the dinosaurs, remains poorly understood. Some researchers have proposed that a burst of radiation from a nearby cosmic event could have stripped away part of the protective layer high in our atmosphere that shields the surface from harmful radiation. Without that shield, life at the surface and in the shallow seas would have been exposed, and the damage could have rippled through the entire web of life. We may never know for certain whether this is what happened, but the very possibility is sobering. It means that a planet can be doing everything right, with abundant life and stable conditions, and still be devastated by an event occurring thousands of light years away, an event its inhabitants could neither predict nor prevent. The galaxy, it turns out, is a shooting gallery, and a planet's position within it matters enormously. Worlds too close to the crowded, violent center of a galaxy may be sterilized again and again by nearby explosions, never given enough peace for complex life to develop. Worlds in the quieter outskirts, like our own, may simply be too far from the action, in regions where heavy elements are scarce and planets are harder to form. There may be only a narrow band, a galactic habitable zone, where conditions are just right. Picture our galaxy from above, a great spiral of hundreds of billions of stars, with dense, crowded regions near the center and sparse, quiet regions toward the edge. Near the heart of the galaxy, stars are packed closely together. Supernovae erupt frequently. Radiation washes through the region in waves. The gravity of passing stars can fling planets out of their orbits or rain comets down upon them. It is a dangerous neighborhood, and any world there might be sterilized again and again before complex life could ever take hold. Toward the far outer edge, the opposite problem arises. Stars are sparse, and the gas clouds from which they form are poor in the heavy elements needed to build rocky planets. A world out there might enjoy peace and quiet, but it might never have the right materials to form in the first place, or to grow the chemistry that life requires. Somewhere in between lies a band that is rich enough in heavy elements to form planets, yet calm enough to let them develop in peace. Our own sun sits comfortably within such a band, far from the violent center, but not so far that the cupboard of heavy elements is bare. If this idea is correct, then much of the galaxy is simply off-limits to complex life, and only a thin ring of stars offers a real chance. That alone would dramatically reduce the number of worlds where a civilization could ever arise. And even within that band, survival is not assured. There are subtler cosmic threats as well. The stability of a star over billions of years, the presence of a large planet to act as a shield, absorbing or deflecting incoming debris, the presence of a large moon to stabilize a planet's tilt and keep its climate steady. The protection of a magnetic field to shield the surface from the constant stream of particles pouring off the star. Consider just how finely tuned our own situation is. Our sun is a calm and steady star, not too large and not too small. The largest stars burn through their fuel in a few million years, far too quickly for complex life to evolve around them. The smallest stars are prone to violent flares that could repeatedly scorch any nearby planet. Our sun sits in a comfortable middle ground, shining steadily for billions of years, long enough for life to take its time. Our planet orbits at just the right distance, neither so close that the oceans boil away, nor so far that they freeze solid. We have a large neighboring planet, whose immense gravity helps sweep up or redirect many of the comets and asteroids that might otherwise strike us. We have a single large moon, unusually large for a planet our size, which steadies our tilt and keeps our seasons from swinging into wild extremes. We have a molten, churning core that generates a magnetic field, an invisible shield that deflects the stream of charged particles constantly flowing from the sun and helps protect both our atmosphere and the life beneath it. Each of these features, on its own, might be common enough, but to have all of them together on the same world for billions of uninterrupted years may be extraordinarily rare. Each of these is a piece of an extraordinarily lucky configuration. Remove any one of them, and life might never get the chance to flourish, or might be snuffed out before it ever reaches intelligence. When you begin to list all the conditions that must be met, all the catastrophes that must be avoided, the picture starts to shift. Perhaps the reason the galaxy is silent is not a single dramatic filter, but the accumulation of countless small ones. 1,000 ways for a world to fail, and only the rarest of planets threading the needle through all of them. This idea is sometimes called the rare Earth hypothesis. It proposes that simple life might be common throughout the universe, but that the specific combination of circumstances needed for complex, intelligent life is extraordinarily rare. In this view, the galaxy may be quietly full of life at the simplest level. Microbes clinging to rocks, drifting in alien seas, surviving in the cracks and crevices of countless worlds. Simple life, in this picture, is tough and adaptable and common. But the leap from that simple life to anything more, to creatures large and complex enough to build and think and wonder, requires a cascade of fortunate conditions that almost never all occur together. The right kind of star, the right kind of planet, the right position in the galaxy, the right neighbors, the right protective companions, the right stretch of billions of years without a sterilizing catastrophe. Get all of it right, and you might produce a world like Earth. Get even one thing wrong, and you produce a dead world, or a world where life never advances beyond the microbial. If the rare Earth hypothesis is correct, then the filter is not a single wall, but a long, narrow corridor. A path so improbable that almost nothing ever walks its full length. And we, against all odds, may have done exactly that. There is a quiet beauty in this idea, even as it humbles us. It suggests that Earth is not ordinary at all, but a kind of cosmic rarity. A world where an almost impossible string of fortunate circumstances came together and held steady for billions of years. The right star, the right distance, the right companions in the sky, the right shield of magnetism. The right, long stretch of peace, broken only by catastrophes that, terrible as they were, never quite extinguished the flame of life. We did not earn this. We inherited it, the beneficiaries of a sequence of accidents and stabilities stretching back to the birth of our solar system. If the rare Earth hypothesis is right, then every sunset, every ocean, every living thing is the product of a configuration so unlikely that it may not be repeated for a vast distance in any direction. This would once again place the filter behind us, and would make our existence a kind of cosmic miracle. But notice the uncomfortable symmetry here. Whether the filter is behind us or ahead of us, the conclusion is the same in one crucial respect. We are profoundly, perhaps utterly, alone. Either life is rare and we are among the very few, or civilizations destroy themselves and we are next in line. There is no version of the great filter that fills the galaxy with friendly neighbors. That is the cold core of the idea, and it is why it has unsettled so many of the people who have studied it most deeply. Think about what that truly means. The great filter, in every form, leads to the same lonely destination. If the filter is behind us, we are rare, perhaps unique, the improbable winners of a cosmic lottery that almost no one else has won. If the filter is ahead of us, then the galaxy is a graveyard, scattered with the silent remains of civilizations that climbed as high as we have, or higher, before something brought them down. In neither case do we get the galaxy of our dreams, the crowded, friendly cosmos full of neighbors to meet and learn from. The filter, wherever it lies, ensures solitude. It is a strange and sobering thing to realize that the universe offers us only two options, both of them lonely, and that the question of which one we face may be the most important question our species ever asks. But the great filter is only one family of solutions. There are others, stranger and in some ways even more disturbing, that do not require any filter at all. These solutions suggest that the civilizations are out there, alive and well, and that the silence is something they have chosen, or something built into the very fabric of reality. Let us venture into that darker territory now. Among the most chilling explanations for the silence is one that does not assume civilizations are rare or self-destructive at all. Instead, it assumes they are common, advanced, and deliberately quiet, because making noise is the most dangerous thing a civilization can do. This idea is sometimes called the dark forest. Picture the galaxy not as an empty desert, but as a vast, dark forest at night. In this forest are countless hunters, each one moving silently between the trees. Every hunter knows that the forest contains others, but no hunter can know the intentions of another. Is that rustle in the distance a harmless creature or a predator? You cannot tell. And because you cannot tell, the safest course of action is to assume the worst and to never reveal your own position. In such a forest, the moment you call out, the moment you announce where you are, you become a target. Any other hunter who hears you must now decide what to do. And since they cannot know whether you are a threat, the safest choice for them is to eliminate you before you can become one. In this view, the galaxy is silent, not because it is empty, but because every intelligent species has learned the same brutal lesson. To survive, you must stay hidden. Those who broadcast their presence, who reach out naively into the dark, are detected and quietly removed. The silence is not the silence of an empty room. It is the silence of a battlefield where everyone is holding their breath. In this picture, the great civilizations of the galaxy are not absent. They are crouched in the dark, watchful and silent, each one acutely aware that any sign it gives off could be its last. They do not build vast glowing structures around their stars, because to do so would be to light a beacon visible across the galaxy. They do not broadcast their existence, because to do so would be to paint a target on themselves. They have learned, perhaps through bitter experience, perhaps through cold reasoning alone, that the universe rewards the quiet and punishes the loud. And so they wait and watch and say nothing. If this is the true nature of the galaxy, then our own situation is precarious indeed. If this is true, then our own behavior over the past century has been, to put it mildly, reckless. We have been broadcasting signals into space. We have, on occasion, deliberately sent messages toward distant stars, announcing our existence and our location to anyone who might be listening. In the logic of the dark forest, this is the equivalent of standing up in the middle of that nighttime forest and shouting at the top of your lungs. The reasoning behind the dark forest is built on two grim assumptions. The first is that every civilization wants, above all else, to survive. The second is that resources in the universe, while vast, are ultimately finite, and that a civilization can never be fully certain of another's intentions. From these two assumptions, a chain of cold logic follows. If you encounter another civilization, you cannot know whether it is friendly or hostile. You cannot know whether it is weaker than you or far stronger. And critically, you cannot know how it will grow and change over the long stretches of time involved. A civilization that seems harmless today might, given 1,000 years, become an overwhelming threat. Faced with this uncertainty, and unable to communicate quickly across the vast distances between stars, the safest assumption is the most pessimistic one. In this reasoning, the act of revealing your existence is itself an act of enormous risk. And so, the rational strategy for every civilization is the same. Stay quiet. Stay hidden. Listen, but never speak. And if you should ever detect another, weigh very carefully whether to act against it before it can act against you. If this brutal logic holds across the galaxy, then the silence is exactly what we should expect. There are those who argue we should stop, that we should listen but never transmit, that we should learn as much as we can about the galaxy while revealing as little as possible about ourselves. Whether the dark forest is real or not, the debate it has sparked is a serious one, and it touches on a fundamental question. In a universe of unknown neighbors, is it wiser to be curious or to be cautious? This debate has played out among scientists with surprising heat. On one side, stand those who believe that reaching out is the natural and noble thing to do, that any civilization advanced enough to cross the stars would have long ago outgrown the impulse toward violence, and that fear should not keep us silent forever. They argue that hiding is not only cowardly but futile, since our planet has already been leaking faint signals into space for a century, and a truly advanced civilization could likely detect us whether we intend it or not. On the other side stand those who counsel caution. They point out that we know nothing, truly nothing, about the intentions of any civilization that might be out there. To deliberately broadcast our location, they argue, is to make an irreversible decision on behalf of all of humanity and all future generations based on nothing but hope. Once a signal leaves our world, it cannot be called back. It travels outward forever, at the speed of light, carrying the news of our existence to whoever or whatever might be listening. There is no clear answer to this debate, and perhaps there cannot be one until we know far more than we do. But the very fact that thoughtful people disagree so sharply tells us something important. We are a young species, taking our first steps onto a stage whose other actors we cannot see, unsure whether to call out into the darkness or to hold our breath and listen. There is another solution that is, in its own way, even more humbling. What if advanced civilizations are out there, all around us, but we simply cannot recognize them? We assume that we would know an advanced civilization if we saw one. We imagine spaceships, or radio signals, or vast structures built among the stars. But these are all projections of our own current level of technology. A civilization millions of years ahead of us might be as far beyond our comprehension as we are beyond the comprehension of an insect. Consider how an ant perceives a highway. The ant can walk across the concrete. It can feel the heat of the surface, but it has no concept of what a highway is, what it is for, or the vast civilization that built it. The highway is simply part of the landscape, an unremarkable feature of its world. The gap between the ant and the engineers who built that highway is enormous, but it is nothing compared to the gap that might separate us from a civilization 1,000,000 years more advanced than our own. We have had science for only a few centuries. We have had the ability to leave our planet for only a few decades. Imagine what another few centuries might bring, let alone another 1,000,000 years. A civilization that old would have moved so far beyond us that the very categories we use to think about technology might no longer apply. We search for radio signals because radio is what we know. We look for spacecraft because spacecraft are what we build. We imagine vast structures around stars because that is the kind of engineering we can conceive of. But all of these are reflections of ourselves, projected onto the cosmos. An advanced civilization might communicate through means we have not discovered, build using principles we do not understand, and exist in forms we would not even recognize as life. We might be staring directly at the evidence of their existence and reading it as nothing more than the ordinary behavior of nature. We might be in exactly that position with respect to an advanced civilization. Their technology, their works, even their communications might be all around us, woven into the fabric of the universe in ways we cannot perceive or understand. We might be searching for radio signals, while the real conversation is happening in a medium we have not even discovered. Some thinkers have taken this even further. What if a sufficiently advanced civilization does not expand outward into space at all, but inward, into realms of physics we barely understand? What if they retreat into the tiniest scales of reality, or into engineered pockets of space that are invisible from the outside? A civilization that has transcended the need for planets and stars might leave no footprint that we could ever recognize. There is a version of this idea that is particularly elegant. It suggests that the natural path of an advanced civilization is not outward, into the vast and cold and slow distances of space, but inward, toward ever smaller and faster and more efficient scales. Think about the direction our own technology has taken. Our machines have not grown larger over time. They have grown smaller, faster, denser, more efficient. We pack more and more capability into less and less space. If that trend is universal, then the destiny of an advanced civilization might be to shrink, in a sense, into realms of extraordinary density and speed, where thought and experience happen far faster than anything in the slow outer world. Such a civilization would have little interest in colonizing star systems. The distances would be unbearably slow, the rewards meaningless, to a mind that lives 1,000 lifetimes in the span of a single one of our heartbeats. It would withdraw from the macroscopic universe entirely, becoming invisible to anyone watching for ships and signals. If this is the fate of advanced intelligence, then the galaxy could be full of civilizations that have simply turned inward and vanished from our view. Not gone, but unreachable, living at scales and speeds we cannot perceive. There is even the unsettling possibility that we are not living in a base reality at all. Some have speculated that an advanced civilization might create simulated universes, complete with simulated inhabitants, and that we could be living inside one such creation. If that were the case, then the silence would be by design. The simulation would contain only what its creators chose to include, and other civilizations might simply not be part of the program. Consider the logic that leads some thinkers to take this idea seriously. If it is possible to create a convincing simulated reality, complete with conscious beings who believe themselves to be real, then an advanced civilization might create not just one such simulation, but vast numbers of them. If that is true, then simulated realities would vastly outnumber the one true base reality. And if simulated minds outnumber real ones by an enormous margin, then any given conscious being, statistically, is more likely to be living in a simulation than in the original world. It is a strange and slippery argument, and there is no way to test it from the inside. But if we are indeed living within a created reality, then the empty sky is not a mystery to be solved at all. It is simply a backdrop, painted by whoever made our world, populated with exactly as many neighbors as they chose to include, which, so far, appears to be none. We cannot prove this idea, and we cannot disprove it. That is precisely what makes it both fascinating and frustrating. It sits at the very boundary of science, in a place where observation cannot easily reach. But it serves as a reminder that some of the assumptions we make about reality itself, assumptions so basic we rarely question them, might not hold. The silence we hear might not be a feature of a vast and real cosmos at all. It might simply be the edge of the canvas on which our world was painted. These ideas push at the very edges of what we can meaningfully discuss. They cannot be proven, and many of them may never be testable. But they serve an important purpose. They remind us that our assumptions about what an alien civilization should look like and how it should behave are built almost entirely on the example of ourselves. And we are a very young civilization, taking our first uncertain steps, with no idea what we might become in a million years, let alone what others might already be. We have had the ability to leave our planet for only a few decades. We have had radio for barely more than a century. We have had science, in its modern form, for only a few hundred years. On the scale of the cosmos, we are not even children. We are infants, blinking in the light, just beginning to make sense of the room we have been born into. To assume that our current understanding represents the limits of what is possible, or that our current methods of searching are the only ones that matter, would be the height of arrogance. The truth is that we are trying to imagine minds and technologies that may be utterly beyond us. It is a little like a child trying to imagine the thoughts of an adult, except the gap may be far, far wider. Our failure to detect anyone may say more about the limits of our own perception than about the emptiness of the cosmos. It is humbling to remember just how brief our own existence has been against the backdrop of the universe. If the entire history of the cosmos were compressed into a single year, with the Big Bang on the first second of the first day, then our entire species would appear only in the final moments before midnight on the last day. All of recorded history, every civilization that has ever risen and fallen on Earth, would occupy the last few heartbeats of that cosmic year. And our technological age, our radio telescopes and our spacecraft and our search for others, would amount to less than the final blink of an eye. We are newcomers in the most extreme sense imaginable. To expect that we, in our first century of looking, with our first crude instruments, should already have found and understood our cosmic neighbors, may be a bit like a newborn expecting to understand the conversations happening in the room around it. We have barely opened our eyes. There is a related idea worth considering, one that flips the whole question on its head. What if we are not late to the party, but early? We have spent this entire discussion assuming that other civilizations have had billions of years to arise before us. But there is a perspective in which the universe is, in cosmic terms, still very young. The first generations of stars were poor in the heavy elements that planets and life require. It took time, many cycles of stars living and dying, to enrich the galaxy with carbon, oxygen, iron, and the rest. By this reckoning, the conditions for complex life may only recently have become favorable, and star formation is far from over. The universe will go on producing stars and planets for an almost unimaginable span of time into the future, far longer than it has existed so far. If that is true, then the vast majority of all the life that will ever exist has not yet been born. We would not be the last embers of a dying cosmic fire. We would be among the very first sparks of a fire just beginning to catch. The silence, in this view, is not the silence of a graveyard. It is the silence of a theater before the show begins. The seats still empty, the audience yet to arrive. We might simply be one of the first to take our seat. There is real science behind this idea, not just wishful thinking. The rate at which stars form has been declining. But the universe will continue to make stars for an immense span of time to come, far longer than the time that has already passed. The smallest, longest-lived stars will keep burning steadily for trillions of years, providing stable homes for any planets that orbit them. If life tends to arise around such long-lived stars, then the overwhelming majority of all the worlds that will ever host life have not yet even formed. In the grand timeline of the cosmos, we are not arriving at the end of the story. We are present at its very beginning, in the opening pages, when the ink is barely dry. This is, in some ways, the most hopeful explanation of all. It suggests there is nothing wrong with us, nothing fatal in our path, no filter waiting to end us. We are simply early. And if we are early, then the future of the galaxy, the long story of who fills it with life and voices, may be ours to help write. So where does all of this leave us? We have walked through a gallery of possibilities, each one offering a different answer to that simple, haunting question asked over lunch all those decades ago. Where is everybody? We have walked a long road to reach this question again, and it lands differently now than it did at the start. When Fermi first asked it, it sounded almost like a joke, a clever observation over lunch. But having traced through the possibilities, we can see that it is one of the most consequential questions our species can ask. Buried within it are questions about how rare life is, about how fragile civilizations are, about the dangers that wait in the dark, and about our own chances of surviving the century ahead. Every possible answer carries a lesson, and most of them carry a warning. Perhaps the answer is that life is vanishingly rare, and the great hurdles lie behind us. In that case, we are the survivors, the rare flame that caught, and we may be among the first intelligent beings ever to gaze out at the cosmos. Perhaps the answer is that civilizations are common, but that they destroy themselves, and the great hurdle lies ahead of us. In that case, the silence is a warning, and our greatest challenge is still to come. Perhaps the answer is that the galaxy is a dangerous place, full of hunters who stay hidden, and our reaching out has been a mistake we do not yet understand. Or perhaps the answer is that they are already here, in forms we cannot perceive, going about their existence in ways that leave us as oblivious as an ant on a highway. Or perhaps they are simply quiet, content within their own worlds, with no need to announce themselves to the dark. Or perhaps they are hiding, having learned that silence is the price of survival in a dangerous galaxy. Or perhaps we are early, among the first to arise in a universe that has only just become hospitable to life, with the great cosmic story still mostly unwritten. Each of these answers paints a different picture of our place in the universe. Some are lonely, some are hopeful, some are frightening, and the strangest part is that, right now, we cannot rule any of them out. We do not know which of these is true. We may not know for a very long time. But here is what makes this moment in history so extraordinary. For the first time, We have the tools to actually look for answers. A new generation of telescopes is now capable of studying the atmospheres of distant planets, searching for the chemical signatures of life. This is a genuinely new power in the history of our species. For all of human existence, the question of whether we are alone has been purely a matter of philosophy and speculation, something to wonder about under the stars but never to actually answer. That is changing within our own lifetimes. We are the first generation with the tools to begin moving the question of alien life out of the realm of pure imagination and into the realm of evidence. We can now examine other worlds closely enough to ask whether they breathe. We can send machines to the most promising places in our own solar system and dig into their soil and probe their hidden seas. We can sweep the sky for signals with instruments far more sensitive than anything that came before, processing oceans of data in the search for a single artificial whisper. None of this guarantees an answer soon. The universe is vast, and our reach, though growing, is still small. But for the first time, the search is real. The instruments are turning. And every world we examine, every atmosphere we read, every silent star we cross off the list, brings us a little closer to understanding which of the many possible answers is the true one. If we find a single other world, anywhere, that bears the marks of biology, it would transform everything. How would we even detect such a thing across the impossible distances between stars? The answer lies in light. When a planet passes in front of its star, a small amount of the star's light filters through the planet's atmosphere before reaching us. As that light passes through the gases surrounding the world, certain colors are absorbed, leaving a kind of fingerprint imprinted on the light. By carefully splitting that light apart and studying which colors are missing, astronomers can determine what gases make up a distant atmosphere without ever leaving our own solar system. This is extraordinary. It means we can, in principle, sniff the air of a world circling a star light years away. And some gases are particularly interesting. On Earth, our atmosphere is full of oxygen, an unstable gas that would quickly vanish if it were not constantly replenished by living things. The presence of large amounts of oxygen in a distant atmosphere, alongside other gases that should not coexist without something actively producing them, would be a powerful hint that biology is at work. We do not yet have the certainty we would need to declare that we had found life. A gas that seems like a sign of life might sometimes be produced by lifeless chemistry as well. But the new instruments now coming into use are sensitive enough to begin this search in earnest, examining the atmospheres of distant worlds for the chemical whispers of life. It would tell us that life is not unique to Earth. And depending on what we find, it might tell us where the great filter lies. Here is the strange and counterintuitive part. If we were to discover abundant, simple life across the galaxy, it would be cause for concern, not celebration. Because it would mean that the early hurdles are easy, and that the filter, the thing that stops civilizations, must lie somewhere ahead of us. The more common we find life to be, the more we should worry about our own future. On the other hand, if we search and find nothing, no microbes on Mars, no life in the oceans beneath distant icy moons, no signatures in alien atmospheres, then we might breathe a little easier. There are places much closer to home where we will soon be able to test this directly. Mars, our neighboring world, was once warmer and wetter, with rivers and lakes and perhaps even seas. If life ever arose there, traces of it might still be preserved in the ancient rocks, waiting to be found. Further out, several of the moons orbiting the giant planets hide vast oceans of liquid water beneath shells of ice. These hidden seas, warmed from within and sheltered from the harshness of space, may be among the most promising places in our entire solar system to look for life. If we send probes to these worlds and find them teeming with simple organisms, it would prove that life arises easily, wherever conditions allow. And remember what that would mean. It would mean the early steps are not the filter. It would push the filter forward, toward us, toward our own future. But if we explore these worlds and find them sterile, lifeless, despite having had the water and the warmth and the time, then we gain a quiet reassurance. It would suggest that the spark of life is genuinely rare, that the hardest step lies behind us, and that our long and improbable journey has already carried us past the deadliest part of the obstacle course. A barren galaxy would suggest that the hard step is behind us, that we have already passed the filter, and that the future is ours to shape. In this one strange corner of science, finding nothing might be the best possible news. It is a complete reversal of our instincts. We naturally hope to find life out there, to know we are not alone, to feel the comfort of cosmic company. But the cold logic of the great filter turns that hope on its head. A discovery that would thrill us, the finding of life elsewhere, might actually be the darkest possible omen for our own future. And a discovery that would disappoint us, a lifeless and barren cosmos, might be the strongest possible reassurance that we have already survived the worst. It is a humbling reminder that the universe does not always arrange its truths to match our feelings. There is a profound responsibility hidden in all of this. If we truly are alone, or among the very first, then we are the custodians of something almost unbearably precious. We may be the only place in the entire galaxy where matter has organized itself into a form capable of looking up and wondering. The only eyes through which the universe sees itself. For all its vastness, for all its hundreds of billions of stars and its unimaginable stretches of time, the cosmos may have produced only one place where it became aware of its own existence. One place where matter arranged itself into a form that could look back at the stars that made it and understand where it came from. That place, as far as we know, is here. The atoms in your body were forged in the hearts of ancient stars, scattered across space when those stars perished, and gathered together again to form a world and a sea, and eventually you. In a very real sense, you are the universe, organized into a pattern complex enough to wonder about itself. The only minds that can ask these questions at all. Hold that thought for a moment, because it is easy to say and hard to truly feel. Across the entire span of the Milky Way, across hundreds of billions of stars and the worlds that circle them, we know of exactly one place where the universe has woken up and begun to understand itself. Here, this pale world, this thin film of life clinging to the surface of an ordinary planet, circling an ordinary star, in a quiet corner of an ordinary galaxy. Every poem ever written, every piece of music ever played, every act of love and discovery and wonder in all of known existence has happened here, in this one fragile place. If we are alone, or nearly so, then everything that has ever mattered to anyone, everything that ever could matter, depends on the survival of this single thread of life. That is a weight almost too heavy to imagine. But it is also a source of meaning almost too profound to express. If that is true, then our survival is not just our own concern. It may be the difference between a galaxy that one day becomes filled with life and meaning and a galaxy that remains forever silent and dark. We would be, in the most literal sense, the seed from which a living galaxy might one day grow, or the spark that flickered out, leaving the dark unchanged. That is a responsibility unlike any other, and it falls on us not because we chose it, but simply because we happen to be here, now, aware of the stakes. Every civilization that came before us, if any did, has fallen silent. We do not have to. The great filter, if it lies ahead, is not a law of nature like gravity. It is a challenge. A series of choices about how we handle our own power, our own conflicts, our own fragile world. The same intelligence that could end us is the intelligence that could save us if we choose to use it wisely. This is what separates us from a rock falling toward a planet or a star exploding in the dark. Those are blind forces, indifferent, governed only by physics. But we are not blind. We can see the dangers ahead of us. We can name them, study them, and work to avoid them. No species before us, as far as we know, has ever been able to do that. The dinosaurs never saw the asteroid coming. But we have already found the asteroids, mapped many of them, and begun to imagine how we might one day turn one aside. We can recognize the gap between our power and our wisdom, and we can choose to close it. We can build technologies and also build the restraint to handle them. This capacity for foresight, for deliberate choice, may be the single most important thing about us. It is the one thing that could allow a civilization to do what perhaps none before it has managed. To see the filter ahead and to step around it. We are, in a sense, taking a test that countless others may have failed. The empty sky is not just a mystery to be solved. It is a mirror reflecting our own possible futures back at us. When we ask why the universe is silent, we are really asking what becomes of a civilization like ours. Do we learn to manage our power, to resolve our conflicts, to protect our world, and to step out among the stars? Or do we join the long, quiet procession of those who reached this point and went no further? The answer is not written yet. It is being written now, in our own time, by the choices we make. In its silence, we can read either a warning or an invitation, a warning that the path ahead is treacherous and that we must tread carefully, or an invitation to become the first, the ones who make it through, the ones who fill the quiet galaxy with voices at last. And perhaps the choice between those two readings is, in part, up to us. The universe will not decide for us whether we survive our own adolescence as a species. No outside force will save us from the dangers we create, and none will doom us either, except through the slow, indifferent processes of physics that we may yet learn to outwit. The asteroids can be tracked, the technologies can be governed, the conflicts can be resolved, the home world can be protected. None of these things are easy, and none of them are guaranteed, but they are possible. And possibility is everything. A civilization that understands the filter ahead of it has already taken the first step towards surviving it. We are, right now, in the rare and precious position of being able to see the dangers before they arrive. That foresight is a gift that perhaps no species before us has ever possessed in quite the same way. What we do with it will write the next chapter of the story, not just for ourselves, but possibly for the entire galaxy. The terrifying solution to the Fermi paradox is not any single answer. It is the realization that every answer points to the same fragile truth: that intelligent life is precious beyond measure, that its survival is far from guaranteed, and that we may be carrying the only spark of it for light years in every direction. Whether the filter lies behind us or ahead of us, whether the galaxy is empty or merely hidden, whether we are the first or the last, the conclusion converges on a single point. What we have is rare. What we have is fragile. And what we do with it matters more than we can possibly know. The next time you look up at the night sky, consider the silence, not as an absence, but as a question being asked of us. Look at those distant points of light, each one a sun, many of them circled by worlds we will never visit. Somewhere out there, around one of those stars, the same drama may have played out that is playing out here. Life may have stirred, intelligence may have awakened. A civilization may have looked up at its own sky and wondered the very thing we are wondering now, and then fallen silent. Or perhaps not. Perhaps the silence means that we are among the first, and that the great story of life in the galaxy is only just beginning, with us at its opening. We cannot yet know which it is. But we can choose how we carry the knowledge of the question. Of all the worlds that may have tried, of all the civilizations that may have reached for the stars and fallen short, we are still here, still curious, still listening, still here, against the odds, asking the question. Think of all the maybe civilizations hidden in that silence. The ones that may have arisen on ancient worlds billions of years before us and reached for greatness and fallen. The ones that may have looked up at their own night skies and asked the same question we ask and never found an answer. The ones that may be out there right now, hidden and afraid, listening as we are, wondering as we wonder. If any of them existed, they are gone or silent now, and we cannot hear them. But we are not gone. We are here, on this small world, at this particular moment, with our eyes finally open and our instruments finally turning toward the dark. We carry within us the curiosity that drove every one of those lost civilizations, and perhaps, if we are wise, the foresight that they lacked. And perhaps, if we are careful and wise and just a little bit lucky, we will be the ones who finally answer the question that has echoed across the cosmos for so long. Where is everybody? Maybe, one day, the answer will be us. Maybe, after all the searching, after all the silence, the first voice the galaxy hears clearly will be our own. Maybe the empty sky has been waiting, not for us to find someone else, but for us to become the someone that a future civilization will one day find. If we survive, if we are wise, if we choose, again and again, to step around the dangers that may have ended all the others, the question that echoed across the cosmos for so long may finally have an answer, and that answer may be the quiet, stubborn, hopeful persistence of a single species that refused to fall silent. Subscribe for more journeys into the cosmos. And remember, in a silent universe, you are the voice that wonders why.